Oke, Assalamualaikum warahmatullahi wabarakatuh. Welcome back to process transport class, and this one is the last topic that we're going to discuss, and we're going to discuss about the one-dimensional heat transfer processes. Start with the conduction one. If you still remember, then we have in here a Fourier law, so that the Qx in here is the flux of conduction. The flux itself is actually Qx xn divided by the A. So if you are going to calculate the heat transport rate, then the value is Qxnx. But if the heat transfer is a constant at the certain surface area, so the Qxnx is divided by the A, the value is constant, and it can be calculated by using minus K dt over dx, and this one is called as flux. Yeah, so you don't have to be afraid to misplace the definition about the Qx and the Qx over A. Qx over A is a flux, and the Qx itself is the heat transport rate. So for the steady-state heat transport problem, no generation constant area, the equation will become something like this. So this one, the Qx over A is a constant, and you can integrate the equation from this one, minus K dt over dx. So if I write down the equation, Kx over A is equal to minus K dt over dx. So the dx will go to the left side, and the minus K dt will be integrated at the right side. So this one is the integration of the x, and this one is the integration of t from t1 to t2. So this is the final equation for the heat transport problem with no generation and also at the constant area. So Qx over A is equal to Kx2 minus x1 multiplied by T1 minus T2. So what about if the K value is not constant and it fluctuates linearly with the temperature? So you can use this equation. Qx over A is Km. So you can find out that in here you find a new variable which is Km. Km itself is the mixed conduction constant, and the Km itself has an equation of A plus B multiplied by T1 plus T2 over 2. So the value of A and B in here, you can get it from any journal, any book, or any references. So T1 and T2 is the temperature. This one is for the example of the constant area heat transport. Calculate the heat loss per meter square of surface area for an insulating wall consisting of 254 mm of fiber insulating material with the K of 0.0848 watt per meter Kelvin, where the inside wall temperature is 353.7 and the outside wall temperature is 297.1 Kelvin. So you can just easily use this equation. You can just insert the value for the K, x2 and x1. So the K is 0.048, and then x2, the insulating material is the wall is 254 mm, so the value is 0.254 multiplied by the temperature difference, which is 352.7 and 297.1, and the value is 10.51 watt per meter square. This one is the heat loss per meter square. That one, if the question is the heat loss per meter square, then it means that you have to calculate the flux. But if the question is about the heat transfer rate, then you have to calculate the Kx. So you have to find out the surface area of your heat transport. And this one is the thermal conductivity. It is just the value of the thermal conductivity. Of course, there are three type which is gas, liquid, and solid, and you can just find the value itself at the references book or any journals. Next is the convection. The convection equation is Q is equal to heat transfer coefficient of convection multiplied by the surface area, heat transfer area, and also the TW minus TF. TW in here means that the temperature of the wall or temperature of the surface area, and then the TF, this one is the F, yeah. TF is the temperature of the fluid or average temperature of the fluid. So this one is the range value of the heat transfer coefficient of the convection for a different mechanism like condensing steam, condensing organic, boiling liquid, moving water, still air, and moving air. What about the process? If we have a process in the conduction through the empty cylinder, so we have a cylinder in here, or like this. This is the image from the top, and then the fluid flows at the center, and the conduction goes through an empty cylinder. So this cylinder is empty. So you can just write down the general equation where QR divided over A is equal to minus K dt over dr, but you have to make sure that the A in here is in the 2πr times L, which means that the surface area of the cylinder. So we use the surface area of a cylinder 2πr L. So by inserting this equation to the A and then you integrate the equation, you will get this equation for the conduction through an empty cylinder. And once again, in here you will find out new variable which is ALM. ALM in here is a surface area of a mean surface area logarithmic, mean and logarithmic, where the ALM in here is this one, 2πLR2 minus 2πLR1 divided by ln 2πLR2 divided by 2πLR1, or A logarithmic or A mean logarithmic is A2 minus A1 divided by ln A2 over A1. So this is what you have to make sure that when you are using a calculation for the conduction in a which is through the empty cylinder, you have to find out the radius of your cylinder itself, so you can easily calculate the flux or the heat transfer rate. This is an example: a cylinder tube made of rubber with an inner radius of 5 mm and outer radius of 20 mm is used as a cooling coil inside the bath. Ice water flows through this tube, and the inner wall temperature is 274.9 and the outer wall is 297.1. And how long a tube is needed if you want to remove the heat of 14.65 watt? So like what I showed previously, we have a tube in here. The outer diameter is 20, and then we have another cylinder in here, and the inner diameter is 5. So the fluid is flowing between the cylinders, so between the cylinder with the inner wall temperature is 274, so this one is 274, and the outer temperature is 297. So how to calculate the length of the tube? Then you can just write down the original equation first. Oh, I forgot that the solution is not I didn't write down at the slide, so you can just try by yourself by inserting all the known variable into this equation. Yeah, so you have to find out the R1 first. Yeah, you have to write down the R1, R2, and then the A1, A2, and then you will get the value of Q, and then Q total divided by the Q will be equal to the length of the pipe needed. Yeah, so you will get unit information of R1, R2, T1, T2, L is also there, Ke is also there. Then you will get the Q, X, and R, or the heat rate, and then you divide the key total divided by key R, you will get the length. So this one is the second. The first one is the conduction through an empty cylinder, and then the next one is the conduction through the empty ball. So we have a ball. The equation is still the same, but what is the difference between this one and with the previous one? The surface area, of course. Now, since we have a ball, the surface area will be 4 multiplied by pi multiplied by r square. And after that, you will integrate the equation left and the right. Left side integrate by the r, right side integrate by the t. So we'll get this equation for the conduction through an empty ball. You have a ball in here and a smaller ball inside the ball, and then at the middle of this one is an empty. So this one is the conduction of an empty ball, means that. This one is the AM, and then the AM in here is A1 times A2, and then power half, root of the A1 times A2. Next, we have a conduction through the multiple layers of the flat walls. So you can imagine that we have 3 different wall with a 3 different material. Means that the resistance will be much higher rather than when you are going to remove a heat from a material with only one type of the material. So it means that in here we have 3 different walls, and let's say the source heat is from here, and then you want to remove it to this side. So it has another 3 resistance in here. So the Q total itself, the Q of the resistance is Ka times A divided by delta XA multiplied by T1 minus T2, or the QR, you can, if you find the temperature at the inside and outlet of the temperature outside of the wall, then you can just combine the equation into this one, where the QR is T1 minus T4 over delta XA over KA time plus delta XB over KBA plus delta XC over KCA, or it can be easily written by the delta T divided by the resistance, total resistance. So if we have more than one walls or more than one resistance, then you have to make sure the total resistance itself. You can calculate by using this one, RA plus RB RC. This is the example of a refrigerated room which has a walls made of layer 2 and 12.7 mm pine wood, and then 101.6 mm of styrofoam and 76.2 mm concrete. So we have a room in here, and then we have 3 different walls. This one is the A, B, C, and then this one is the room. The A is the pine wood, B is the styrofoam, and then C is the concrete. And then the inner wall temperature of the room is 255.4 Kelvin. The thermal conductivity value of the A is known, Kb is also known, Kc is also known. This one Ka, Kb, and Kc. You have to calculate the rate of heat loss. Yeah. So the key, and then the temperature at the boundary between the pine wood and the cork. And oh, sorry, this one is the styrofoam. Yeah? Is the styrofoam between the pine wood and also the styrofoam? So the temperature at this one. So this one is T1, T2, T3, and also T4. So you need to find out the value of T2. First, I think there is a missing information. This one is the outlet. So the inlet is 255.4 and at the outlet is 297.1. So by using this equation or the previous one, where the key is delta X over the sigma of the resistance, and you have to calculate its resistance RA, RB, and RC. RA is for the pine wood, RB is for the styrofoam, RC is for the concrete, for the concrete. By using the known variable delta XA is already there, Ka is there, A is also there, so you will get the value of RA, RB, and RC. And then by using the equation of Qx, then you will get the value of the heat loss, which is 16.48 watt or 56.23 BTU per hour. And if you want to calculate for each wall, then you can use this equation where the QR is equal at each material. So if you want to calculate the QR at the first material, then the equation is this one: Ka times A divided by delta XA multiplied by T1 minus T2. So you will get 255.4 minus T2 divided by 0.0841 from this one is equal to 256.7. So this one is 255, and then at this one it will become the 256. So that one is quite easy to find the heat loss and also the temperature at the middle of the 3-layer material. Number 4, in here we have the conduction heat transfer in a cylindrical layer. The equation is almost the same, but what are the difference? The difference in here we have ALM. So the surface area, since we are using a different layer of a cylinder, so we use the surface area of mean logarithmic of surface area. Yeah. So let's say if we only have like this one, means that this one is the R1, R2, and this one is the inner, this one is at the outer. This one is for the example, a steel pipe with the K of this one, yeah, K1 let's say, with an inner diameter of 0.0254 and outer of 0.0508. So we have like this one already. This one is 0.0254 and at this one is 0.0508, is covered with a layer of asbestos. So it's still added with a layer of another cylinder with the thickness. So the thickness itself means that the addition of the radius. Yeah. So this one is the 0.0254. Oh, the first one is still diameter, so this one is diameter and this one is the diameter. So you have to make sure that the value that you are going to use is in the radius, yeah, so that you can use the previous equation, unless you want to calculate new equation. So in here we have information that the inside temperature is 811, and the outside temperature at this one, the temperature is 310.8. You need to calculate the heat loss for a length of 0.304. So the length of the cylinder, so let's say it is a horizontal, then the length is 0.304 meter, or 30 centimeter, and you need to calculate the temperature between the metal and the insulator. So if this is the metal and this is the insulator, so this temperature, the temperature at this one, if this is the inner T1, and then this one is the T2. First, yeah, you need to find the radius of each material, and then you calculate the A each of them, and then the mean logarithmic surface area by using this equation. So we have 2 surface area mean logarithmic, and we have 2 resistance. Yeah, you calculate the A, and then A logarithmic, and then resistance, and then you can calculate the Q. So the Q itself in here, the value is going to be used to find the temperature between insulation and also the metal, and the value of the temperature is 805.5 Kelvin. Last one, I think this one is the last. The conduction through the connected parallel material. So in here we have 2 different sources, T1 and T3, and then at the outlet we have T2 and T4, while the material itself, which is gone through, is combined from 2 different materials, which is A and B. So the Q itself will be look like this. QT is equal to 1 over RA plus 1 over RB times T1 minus T2. This is the condition when the T1 is equal to T3 and T2 is equal to 34. If the temperature is different, then you have to still use the equation, the original equation, this one. This one is the last one. Yeah, this one is the last one. So we have a combination of convection and conduction. This is where you are going to find out the new term, which is overall coefficient. So if I have a slab in here or any metal, and then this one is an open air and this open air, so the heat transfer from this point or to this point is going to be convection, conduction, and also convection. So the temperature difference or the temperature reduction from point 1 to point 2 is going to be in the convection process. The transfer at the metal is going to be a conduction process, and at the surface of the metal until the point 4 it will has a convection process. So the Q itself for the first one is Hi times A times T1 minus T2, and then for the conduction it is Ka times A over delta X times T2 minus T3, and then the convection, last convection is Ho. This one is the inner, and then this one is the outer. So this is what we got for the total resistance. Sigma R is 1 over Hia, delta X over Ka, and 1 over Hoa. So this is what we know as the overall heat transfer coefficient. U is equal to 1 over 1 Hi plus delta X over Ka plus 1 over Ho, and this one is the term for the cylinder. The difference is only at the Ro, the delta X. Yeah, the delta X in this one we are using the outside radius and also the inner radius. This is the example for the combine conduction and convection process. You can just easily follow step by step. This one is the number 1, number 2, 3, 4, and step number 5. Oh, there is still another one. This is what if the conduction is followed with the heat generation. So you have to write down the first equation, which is still has the steady state term and also the Q generation. So since the process is steady state, so this one is equal to 0. What is left is 1 over a dq over dx plus q. And then if you integrate, you differentiate again, double differentiation, the qx itself it has also dt over dx. So the equation will become d squared t over dx squared plus q over k. So this one is the integration final result, where t is minus q over 2k x squared plus c1x plus c2. So you can simplify the equation by using two different boundary condition, for boundary condition 1 and 2, and then this one is the final equation that can be used for the conduction process with heat generation. I think that's all for the conduction process of the Tafa phenomena, and I think that's all. And then any other information I will let you know from the WhatsApp group. Thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.